Hello, this is the demo for the third assignment. Third assignment's first collab, where we had to create a collab now, notebook only using, we have to create a 3-layer deep neural network for non-regression problem. And we had to do manual backdrop and the chain rule based on gradient propagation, and use TensorFlow Einstein summation instead of matrix multiplication, and generate synthetic data using the equation, and plot it using 4D plot. So this is my notebook. So in this we are initializing the weights using NumPy, and then we are using TensorFlow's Einstein summation, and no Keras or AutoGrad was called. For this, as the assignment mentioned, that we have to use 3 layers. So we have 3 hidden layers, 1, 2 and 3. So in the first one we have 64 neurons, 34 neurons, and then 16 neuron, and the activation functions used are dan, relu and edu. And then we have one output, and there is no activation applied on top of it. And the equation which we have used is this. It's a complex equation, but so this is just the initialization. Then this is the synthetic data generation. So using the equation I earlier showed, this equation, we are creating random numbers, and then we are creating random numbers based on that equation. And we did introduce some noise in the data. Now this is now that as the data is generated, we will now scale the data, normalize the data, and then split into train and test. So we are normalizing it, and then we are splitting the data, so 80% testing and 20% training. So this is how we split the data. Now let me show you how we had to do a 4D visualization using PCA. So as the equation has 3 inputs, x1, x2 and x3, let me just go x1, x2 and x3. So what we did is we used 2 principal components, and the third variable while plotting was y, and it was encoded as the color. I'll show you. So here we are setting the components as 0. So even though it has 3 inputs, it will reduce it to 2 components, and so this is how the plot looks like, the 4D view looks like. So we have principal component 1, principal component 2, and this is the on the z-axis you can see the y normalized, and that the color shows the value of y. So the color blue color related to blue are towards 0, and the values above are are increasing like that. So this is how the data looks right now, and this is the target distribution. So the target values is mostly skewed towards 0 to 5, as you can see. Then this is how the data looks. Now let's move to the second part, which is weight initialization. So again, for weight initialization, we excuse me, just a second. So for weight initialization, we have these 2 initialization schemes which we have, which is Xavier's and Etchy, which is also known as K-meaning. So Xavier's we use when when we want to keep the variance of activations roughly the same from layer to layer. So this is useful when we are working with tan and sigmoid. That's why I have used it in weight 1, because if you remember, for first layer we are going to use tan as an activation. So that's why I have used Xavier here. And HE is the same thing, but it is used when we are working with the ReLU type activation. That's why in the later layers I have used HE initialization. And the idea is it uses a slightly larger variance so that after ReLU the activations still have healthy scale. So because we do put all the negative values towards 0, so the variance changes a lot. So yeah, that's why we do that. Then yeah, so this is how the weights are initialized. And the biases are just using numpy's zeros function. Yeah, so initially we are putting everything as 0, and then we will using backpropagation the values will change. Then we have the activation functions. Yeah, so this is the activation function, and this is the derivative. It's derivative, so that using when we are doing the backpropagation it's easy to use, so that's why it is used. It is created. So we have created ReLU and LUF. Yeah, after that we are creating a as the assignment mentioned, that we have to use Einstein summation and not matrix multiplication. So we have used it over here. So Einstein summation is shorthand notation for summing over repeated indices in tensor expressions. So yeah, so basically it makes tensor equations shorter and less cluttered, as I have mentioned in the previous assignments as well. So we just have to give this notation, and the TensorFlow will take care of the operations in backend and give you the output in the same format. You just have to pass the tensors on which you want the operations to perform. So yeah, this is the Einstein summation, which will do the matrix multiplication for us. So here ij are going, and we will get ik. Then yeah, this is just a summation check. It's just a check whether the function is working fine or not. Then we have the forward pass. So in the forward pass is where we define how the layers will be called one after another. So yes, so it will take input weight 1, weight 2, weight 3, weight 4, weight 5, weight 4, and bias 1, 2, 3, 4. And in the first layer, what we want is we want to matrix multiply x and w, and then add the bias, and then apply the activation function on top of it, and give the output as z1. Sorry. Yeah, this will get executed, and this then passed into activation function, and a1 will be the output. Now a1 will be input to the layer 2, so that's why we are matrix multiplying a2 with w2, hiding the bias, and then we'll pass the z2 to activation function, and we'll get a2. Then a2 will be matrix multiplied with the third layer's weight, bias, add with bias, passing with the activation, and then we'll get a3. And a3, in that we will again matrix multiplied with the weight force and bias 4, but there will be no activation, as it's a regression problem, so we don't have to do that. Now we got that in z4. Yeah, so this is how the forward function will look for us. Now let's look at the backward pass. So in the backward pass, we have, as the assignment mentioned, we have to do it manually. So what I did is we created this function with we'll pass y hat is the predicted, the value which we predicted, and z1, z2, z3 sorry, W1, W2, and the weights. Uh, uh, the weights and the cache. The cache has the input Z1, A1, A2, A3. Basically, each inputs, each layers input before activation and after activation. So yeah, this is the main. This is the partial derivative uh, of the loss function which we had. So in the regression, the loss function is mean mean of you know y predict y hat minus y, which is original y whole square. So the derivative of it is this. So we'll start with this, and then we'll matrix multiply A3's transport with dz4. That will give us d4 dw4, and then this dw4 will be we'll do np dot sum, and that will give us db4, which is partial derivative for d bias 4. Then again the same will back propagate to layer 3. This was output layer, then it will go to out layer 3, layer 2, and layer 1. So in layer 3 it will go z4, and we will matrix multiply it with w4's transpose. Then we'll get a3's partial derivatives. Then we will do a3 multiplied by activation function. We will get dz3 dz4 like that, and then same thing will happen till we reach to layer 1 and we get derivative for all the values. We'll keep it in a dictionary format. So this is how the back propagation is working under the hood. Yeah, now let's move to the training loop. So in the training loop, we will need the epochs, batch size, learning rate, momentum, and like log properties like that. So for now we are setting the epochs at 500, batch 128, learning rate as this, and momentum. So yeah, we'll start with with epoch, and you'll just randomly permit which create batches basically, and then start the training. So we'll call the forward function, and we'll get the y hat and cache. Cache is basically the values of each layer's input before and after activation. Then we have this loss, which is mean of y hat minus yb whole square, and then we'll do the epoch loss, and then we'll call the backward backward, which will calculate the gradient for us, which we have created the over here. So it will calculate the gradient and store it in grads, and then yeah, again then it will change the values of the weights and biases in place using the momentum and the learning rate, and we'll change these values in the dictionary which we had. Now this is how the backward will work, and then we'll again we'll find the losses, and we'll just print how it works after each epoch. So here you can see the train loss and test loss. So earlier the train loss was quite high, but then as the epochs are increasing, the loss is reducing. Same over here. So now let's see the plot of it. So here you can see the loss and versus epoch, each epoch. So each epoch, earlier the loss was really high, but eventually it went down, and this is in log scale, but you can see that in the training performed really well, but in the test a bit, but it is fine. It is not, if the gap is huge, then we have the problem of overfitting, but this worked really fine. Yeah, so this is just the plot of R2. So here also see, this is the predicted line, and we very much predicted within, near to the line, and I think it should be 99. Yes, the R2 value is 99%. Then this is the residuals. This is also the plot in so this is true y, this is the predicted y, and these are the errors. And in the errors you can see there are a lot of lower values, like around 1 you can see, but very few, 1 2 3, like very few, only 5 6 are which are above, which are high error values. So yeah, that is pretty much in this notebook. Thank you so much.